Welcome you all to Mickey's Study Circle channel. In this video, we shall see how to do the modeling and stress analysis of a rectangular plate with a circular hole under the plane stress using ANSYS APDL. Before we move on to the problem statement, let us have an overview of what is meant by plane stress. The condition of plane stress occurs when all of the stresses acting on the component are in the same plane. As you can see in the figure here, the component of the stresses acting are in the xy plane alone. The stresses acting in the z direction are considered to be zero. Both the normal stress and the shear stress components are assumed to be zero. That is, the sigma z and the tau xz and tau yz stresses, which are the shear stresses, one component of normal stress and two components of shear stress are considered to be zero. This is how, using the condition of the plane stress, a given 3D problem can be converted to a 2D problem. Thus, a 9 element matrix can be converted to a simple 4 element matrix and can be solved. So, this is the advantage of considering the plane stress condition. This condition of plane stress is suitable for doing the analysis of the thin-walled pressure vessels and the thin gear structures. With this knowledge of plane stress, we shall see the problem statement and do the analysis of the problem statement using the strength of material approach and as well as the ANSYS approach. The problem statement goes like this. There is a plate with a circular hole and it is subjected to a tensile load of 2000 Newton magnitude. We need to find the deformed shape of the hole and also need to determine the maximum stress distribution along the AB, that is, in one half of the circle. Considering the thickness of the plate to be 1 mm, the Poisson's ratio to be 0.3 and Young's modulus of the material of the plate to be 210 GPa and the diameter of the circle is 10 mm. Also, the width of the plate is 60 mm and the height of the plate is 40 mm. With this input, we shall see how to determine the stress that is distributed in the plate which is subjected to a tensile load of 2000 Newton load. Taking inputs from the problem statement, the domain of the problem is structural because this is a mechanical member which is subjected to mechanical forces. And the element type that we shall consider to model and do the analysis using the ANSYS APDL is quad 4 node 182, simply called as plane 182 element. The Young's modulus of the plate is 210 MPa, the length of the plate is 60 mm and the height of the plate is 40 mm, its thickness is 1 mm, the magnitude of the load which is acting on the plate as shown in the figure is 2000 newtons and the nature of the load is tensile. With these input, now let us see how to solve this problem using the strength of material approach. These are the parameters that we need to determine. We need to determine the maximum stress, the deformed shape of the hole, and the stress distribution along the half portion of the hole. Let us have an insight into the problem solution by the strength of material approach. For this, the data handbook referred is K. Mahadevan and K. Balavira Reddy to determine the transverse stress around the hole in a plate of infinite width. Using this condition, we shall see how the maximum stress is calculated. The maximum stress sigma max is given by sigma into Kn, where sigma is the average stress. The average stress is given by the formula P by W minus 2 into R into T. As you can see from the figure here, P is the load which is acting on the plate, R is the radius of the hole, W is the height of the plate, and T is the thickness of the plate. So from the parameters from the problem statement, the value of W is 40 and the radius is 5 mm, 2R is nothing but the diameter of the hole and it is 10 mm and the thickness of the plate is 1 mm. The magnitude of the load acting on the plate is 2000 newtons. So substituting the values of these in the sigma average formula, we get the average stress value as 66.6 Newton per mm square. But the maximum value of the stress is calculated by multiplying the average value of the stress with the stress concentration factor Kn. Now let us see how the value of this Kn is determined. To determine the value of the Kn, we shall use this graph which is having K along the y-axis and the ratio of the diameter to the width of the plate in the x-axis. The ratio of the diameter of the hole to the width of the plate is 10 by 40 mm. So corresponding value is 0.25, the ratio is 0.25. So considering the value of 0.25 and taking the line which is intersecting this blue line, as you can see, okay, the corresponding value of Kn is determined and it is found to be 2.45. So if we multiply this average stress value with the stress concentration factor, then the maximum stress that is subjected into the plate having the hole is 163.17 Newton per mm square. Now we shall see how the same problem can be modeled and analyzed using the ANSYS APDL software. Select Mechanical APDL from the Start menu. Before we begin with creating the file, we shall erase the log files of the previous sessions. To do so, from File menu, select Clear and Start New and tell Do Not Read File and OK. And yes, you need to delete all the previous input and start a new database. So tell yes. So with this, we have cleared the log files of the previous sessions. Now, we shall assign the title name for this particular APDL coordinate system. So for that, select File, change title and assign the title name as Plane Stress Problem. Tell OK. Right click and select Fit. So you can see that the title name shall appear in the screen. So to save the work, select Save As from the File menu and in the suitable folder, save the work by giving a suitable file name. Now we shall begin with the problem. Select Preferences and select the domain in which the problem will fit itself. So it is the structural and we need to follow the H method of interpolation. OK. Preprocessor, element type, add element, add, select solid and from this drop down select quad 4 node 182, which is nothing but the plain 182 element as discussed earlier. Okay. In this window, element types window, from the options, element behavior K3, in this drop down select plane stress with thickness so that we can assign the value of thickness to the plate. Okay, and close this window. Real constants, we need to assign the thickness, add. So the element that you have already defined in the previous step is plane 182. For this we need to assign the thickness, which is 1 mm as per the problem statement. Till OK and close this window. Now we shall assign the material properties. So for that, from the material properties drop down select material models and material model number 1 is in which we are going to input the material model details: structural, linear, elastic, isotropic, and input the values of the Young's modulus as 2.1 E5 and Poisson's ratio as 0.3. Tell OK and exit this window. So now we have defined the element, assigned the thickness and assigned the material properties. Now we need to create the model. So to do so, select modeling and from modeling select create. Here we shall not create the model by using the key points. Instead, we shall create the model by using the area options. So for that, select areas and here by default rectangle and circle both are available. Select rectangle and by two corners. So in this window, assign the width of the rectangle which is 60 mm and the height of the rectangle which is 40 mm as per the given data. Tell OK. So now you can see that the rectangular plate of height 40 mm and width 60 mm is generated. Right click, fit, or you can just zoom out so that you can see the rectangle in the screen properly. And now select circle, solid circle, and we shall assume that the circle center point shall coincide with the centroid of the rectangle. So to locate the centroid of the rectangle, it is nothing but the intersection of the two diagonals of the rectangle. So it is nothing but the center. So that is half of the width and half of the height. So 30, 20 is where the centroid of the rectangle shall lie and that shall also be the center of the circle. And the radius of the circle is 5 mm because the diameter as given in the problem statement is 10 mm. Tell OK So now you can see that the circle is created. But as per the problem statement, it is a circular hole in a rectangular plate. So we need to generate a hole. So how do we create a hole? Go for operate, select booleans and subtract areas. So now you can see that in the prompt window, there is a option for entering the base areas from which it has to be subtracted. So this is the rectangle. So I'll enter it as 1, and I shall also enter the area that has to be subtracted by assigning the number 2. So by default, the software would have taken the area 1 as rectangle and the area 2 as circle. So I need to subtract area 2 from area 1 so that I get a circular hole in the rectangular plate. With this, the geometry is completed. So remember, we use the operations of create areas and operate booleans to create the geometry. Coming for meshing, select mesh attributes, picked areas, and select this geometry. Tell OK, and just cross verify if all the inputs that you have assigned in the previous steps are matching with this. The material number is 1, which is from material properties. The real constant set number is 1, which is having the value of the thickness. Then the element type number is plain 182 element, which we have defined using the element type option. We have not created the geometry using the coordinate system, so it is showing 0, and we have not created any sections, so it is showing none defined. Till OK. Now we shall go for creating the discretized model of the given geometrical model. So for that, select size controls, manual size, areas, picked areas, and pick this geometry till OK. So enter the element edge length as 2 till OK. That is, each side of the element shall be divided into 2 equal parts. Now come for mesh option, select areas and select free, and again select this geometry and tell OK. So you can see that the given geometrical model is now created into the FE model by the process of discretization. Now we are more interested towards getting the stress distribution in this circular hole. So for that, we need to have a refined mesh in this particular region. So to create a more refined mesh, what we shall do is we shall select the mesh tool and select refine from this window and pick the circle option and just create a circle by dragging the mouse button and creating a circle. So you can see that the circle is created, and now we shall input the software to create a more refined mesh in that particular region by assigning the value of 2 till OK. So now you can see that a more refined mesh is created in this particular section. So now it is the time for us to apply the loads for the FE model. Select loads, define loads, apply, structural, displacement, on lines, and select the left side of this rectangular plate and arrest all the degrees of freedom by selecting all DOF and entering the displacement value as 0 till OK. So now this particular condition is done. Now we shall go for applying the pressure. Now how do we calculate the pressure? The force is acting on this side of the plate. Okay, the pressure is mathematically the force acting on the given cross-sectional area. So the length or the height of this particular rectangle is 40 mm and it is having a thickness of 1 mm. So the force is acting on this particular face of the rectangle. So the cross-sectional area is 40 into 1, which is 40 mm square, and the pressure acting is calculated by using the force. The force is 2000 newtons. So 2000 divided by 40 is 50 Newton per mm square. So that is the pressure which is acting on this side of the rectangular plate. So to apply the pressure, select structural, pressure, on lines, and select this line. OK, and assign the value of pressure as minus 50. If you enter positive, that is plus 50, then it will be in compressive in nature. So please enter the value as minus 50. Okay, so now you can see that the pressure is acting away from the origin, that is, the force is tensile in nature. Close this. So now it is done with the discretization and the application of the boundary conditions, which is nothing but the degrees of freedom and the pressure. So now let us solve this by using solution solve current load step file till OK. So now if all the boundary conditions and the geometry creation and the meshing is correct, you get this window telling solution is done. So close this file, close. Now we shall view the results. So for that, select general post processor. Under that, select plot results, counter plot, nodal solutions, stress, von Mises stress, deformed shape only till OK. So now you can see that this is the deformed shape of the rectangular plate with a circular hole, and this is the distribution of the stress in the region in which the hole is generated, and this is the value of the stress. So this is the value that we get using the FEA method. But whereas in the analytical method using the strength of material approach, we got the value of stress as 163, and this difference is because of the refinement that is to be done in a much more better way. So if you keep on refining the element in a much better way using better elements, then you approach closer towards the actual solution. So this is the difference in the actual value of the stress and the numerical value, the value that you have obtained by using the numerical method, that is your FEA. So this is the distribution of the stress. So this scale shall detail you the distribution of the stress in this particular geometry. So the maximum stress is concentrated here, as you can see in the hole on this side, that is A and B as given in the problem statement. Now let us see what is the deformed shape. So for that, select plot results, deformed shape only till OK. So this is how the plate is deformed. Now to view the animation of how the deformation shall occur, select plot controls, animate, deformed shape, and reduce the frames to 5. OK. So this is how the plate which is subjected to a tensile load shall deform, which is having a circular hole in it. So you can see that the circular hole is slowly becoming a elliptical hole. So this is how the deformation is going to occur. Close this. And now we need to define what is this distribution of the stress in this particular path, that is A and B, as given in the problem statement. So for that, select path operations, define path by nodes, zoom the geometry. So from this point I shall just pick all these elements. So yes, this completes the first half of the circle, that is the distribution of the stress along the path AB till OK. And we need to define the path name. So I'll define it by using the path name as AB as given in the problem statement. OK. So now this shall detail me what is the number of points that I've selected. So it is around 24 points. File, close, and you can zoom out. Now we need to define what is the stress in this created path. So for that, select that map onto path and select stress, and in stress select von Mises, and the name here is SEQV. So remember this SEQV till OK. Now go for plot path item on graph, and in this drop down select SEQV till OK. So this is how the stress is distributed along the path AB. So as you can see that the maximum stress value as we saw earlier is 160.902, so that is in the path A. Okay, and this is how the stress is getting distributed. So from path A to path B, and this is the circumference, so that is pi into d, so 3.15 into 10. So this value, this is how the stress is distributed towards that region. So this is the value of the stress and this is the distance. So you can save this plot by going for plot controls, hard copy to printer, and select Microsoft Print to PDF and print this graph. So the graph is saved. So this is how the graph can be generated to determine the stress distribution in the path AB. And we can also save the stress distribution. So for that, plot results, counter plot, nodal solutions, stress, select one mysis stress deform shape only till OK. So I can save this, plot controls, hard copy to printer, Microsoft Print to PDF, print, and this is the stress, save. So the PDF copy is saved. So with this, we have concluded on the plane stress analysis problem using the FEA package ANSYS. Finish. You can save the work by clicking Save the database and exit. Thank you all for watching the video.